Okay, I'm going to give you a second. You can pause the video and you can maybe check some of your work up here to check some of these values if you'd like. And then, give me a shout out if you need some help with them. So what about if we turn this table, all the knowledge we learned and all this practice calculations, into like more of a word problem. So calculate the pH of the following strong solutions. Now we should have the strong acids and bases memorized. But you can always just look at a list you have next to you. So I'll just tell you right now these are all strong. So now let's look at this and let's talk about the logic of this. Okay, now in problem A, if I tell you that the HCl is 0.25 molar, how many H's are in HCl? It looks like there's one H in there. So now we can do the negative log of H plus if we're looking to calculate the pH. And since there is one H in HCl, the concentration of the H plus is just this value. So we can just do the negative log of 0.25. So the negative log of 0.25, and you get a pH of 0.6. So pretty low, which makes sense because this is a strong acid. Now what about over here in question B? We have a 0.05 molar H2SO4. Now check this out. How many H's are in H2SO4? And we're going to look at H's at the beginning only. These are the ones that are turning into the H plus in solution. So we have two of them now. So now the pH does equal the negative log of H plus, but the H plus concentration is going to be twice this value because there's two H's in that solution. So I would do 0.05 times 2. So now the negative log of 0.1 is a pH of 1. And if you would have done the negative log of 0.05, you would have probably had a value that's a little bit higher because we're getting an extra H dissociating or splitting apart into solution. We call this a diprotic acid because there's two H's at the beginning. So let's try something similar but different for a base down here. Now, NaOH, what is it? Is it an acid or a base with an OH at the end? Yeah, it's a base. So we're not going to do the negative log of H plus, we're going to do the negative log of OH minus. But if you're doing the negative log of that, you're actually calculating POH equals the negative log of OH minus. So if we do the negative log of this value, negative log of 1e minus 3, we get 3. Now if you're thinking, why is the value low for pH? It's because it's not low. This is POH. So if you want to calculate the pH for the solution, we would need to do 14 minus that. And now does it make sense that NaOH, this base with a high concentration, has a pH of 11? Yeah, that should make some sense now. Okay, the last one. I guess it's the trickiest, but I think I've kind of like taught you how to work your way up to this one. What if I gave you a 0.25 molar solution of calcium hydroxide, this strong base? So now, looking at this, we need to first identify that it's a base. And now we need to kind of look at here and say like, oh wait, look, there's two OHs for every one of these COH2 molecules. So we're going to calculate the POH again because this is a base. So we do that by doing the negative log of OH minus ions. Except this time we're going to do the POH equals the negative log of 0.25 times 2 because there's two OH minus ions dissociated in the solution. So now we do the negative log of 0.5 and that equals 0.3. But again, this is pH, so we need to do 14 minus 0.3 gives us 13.7. Okay, I hope this helped you turn that table into some word problems, and we are comfortable now performing pH calculations.